Hey, this is Jeremy with mycareertech.com, here with another online course for your CareerTech classroom. And today we're going to be discussing the basics of welding, including a short history. We'll discuss the safety and then the proper use of the welding equipment. Let's get started. Welding is the process of joining materials using a source to generate high heat to melt the materials together, which once cooled become fused. Materials that can be joined by welding include metals such as steel, aluminum, brass, and stainless steel, or varieties of plastic or polymer. Although it's taken many forms over the years, the concept of welding has been around since the Bronze Age. Modern welding techniques were first introduced in the 1850s and have led to a variety of different welding processes. One of the most common types of welding is GMAW, which stands for gas metal arc welding. GMAW is commonly referred to as MIG welding, which is short for metal inert gas welding. MIG welding is what we'll focus on throughout our course today. MIG welding was first developed in the 1940s to meet the military's need to weld aluminum, but the process was soon revolutionized to work with steel and a variety of other metals due to the faster welding time it offered. We'll take a look at welding equipment and the process in a moment, but first and foremost, when using any welding equipment, your first priority should be safety. The welding process puts the operator in close contact with a variety of hazards that can prove harmful or even fatal if the proper precautions aren't taken. The first thing to know is the importance of reading and understanding safety data sheets. These are OSHA-regulated documents used to provide information on the dangers and proper utilization of different chemicals that are used day to day. These sheets should be the first step taken when working with a new material. In addition to safe usage of materials, proper storage guidelines should also be followed. Always store gas cylinders upright and away from sources of heat or flame. Anytime gas cylinders are moved, the safety cap should remain on to prevent damage to the valves or explosions. Proper use of personal protective equipment, or PPE, such as welding helmets and goggles, flame-resistant clothing, hand shields, safety glasses, and welding gloves, is essential to ensuring a safe working environment. In modern welding, this includes respiratory protection via filtered masks or respirators, and even supplied air filtration systems. In addition to the welder, any other occupants in the work area should also wear the appropriate PPE. General hazards welders may encounter include exposure to radiation, burns to the operator's skin or eyes, exposure to toxic fumes and gases, and electrical shocks. Intense UV radiation is produced from welding arcs and can cause a number of issues to a welder's skin and eyes, including burns. Any exposed skin can receive the equivalent of a sunburn, and long-term exposure can result in skin cancer. Without the proper eyewear, just a few seconds of exposure to the UV light produced by welding can result in welder's eye, which is an injury or inflammation of the mucous membrane of the front of the eye. Long-term exposure can result in cataracts and in extreme cases, temporary or permanent blindness. Be careful around the welding arc flash as well, as viewing or being exposed to it will result in a feeling similar to having sand in your eyes. Toxic fumes and gases from the chemicals and intense heat can be managed by a properly ventilated workspace or by wearing a respirator. Based on the size of the area, local exhaust or forced ventilation may be employed to keep the fumes and gases away from the welder. This especially includes areas smaller than 10,000 cubic feet per welder or with a ceiling height of 16 feet or less. An electric shock will be produced if the welding operator should come into contact with the electrode in either the ground or the work simultaneously. This essentially puts the operator into the welding circuit. As such, you should never touch the electrode or the electrode holder without the proper ground, PPE, or in wet conditions. Now that you're aware of the hazards that can accompany welding, let's look at the basic process of MIG welding. MIG welding is one of the most popular arc welding methods in the construction and automobile industries due to its ease of use, high deposition rate, and versatility. MIG welding is an arc welding process in which a continuous solid wire electrode is fed through a welding gun and into the weld pool, joining the two base metals together. The source of heat is an arc formed between the continuous metal electrode and the continuous filler metal making contact with the workpiece. The arc is protected by a shielding gas that is also sent through the welding gun. Shielding gas is an externally supplied gaseous shield made up of helium, argon, or carbon dioxide. This protects the weld pool from oxygen, nitrogen, and hydrogen contained in the air. Exposure to these elements can create a variety of problems in the weld. During the welding process, the electrode stick or wire is fed through a welding gun when the trigger is pulled. This becomes the filler metal for the weld. Filler metal, or electrodes, used in MIG welding are measured in diameter and are typically packaged on a spool, reels, and coils ranging from 1 pound to 1,000 pounds. There are two types of MIG filler wire, flux core and solid core. Flux core can be used with or without a shielding gas, while solid core can only be used with shielding gas. An electric arc occurs in the gas-filled space between the electrode wire when contact is made to complete the electric circuit. Electric arcs can generate temperatures of up to 10,000 degrees Fahrenheit. Once the wire electrode and the workpiece come in contact, they become hot and melt, creating a puddle of molten material called a weld puddle. Depending on the materials being joined, the shielding gas then flows through the gun and out the nozzle, resulting in a weld without slag. It's important to note with this process there is no flux or coating in or on the metal electrode. Finally, the welder will watch and manipulate the weld puddle by laying a bead that quickly solidifies into a slag-free metal weld. Laying a bead is like sewing up a seam, but with metal along a joint. Now that we've given a quick overview of how the MIG welding process works, let's explore the equipment and how it's used. MIG welding equipment includes a power source, a wire feeder and gun, a work clamp, and a work lead. The gun itself includes a contact tip, gas diffuser, and a gas cup. If you're using a solid core wire, you may need a gas bottle and regulator. This is because with solid core wire, there's no flux in or on the electrode wire to create a shielding gas to protect the puddle until properly cooled. To get started, you must first connect the work clamp. The work clamp needs to be grounded to the workpiece and must have a good connection. Select the electrode by choosing the type and diameter based on the materials being joined. Then you'll need to select the shielding gas based on the materials, wire, and the position of the welding. Next, turn on the power supply and adjust the machine to remote. Then select the feeder output, which is the wire feed speed, and then the voltage. Finally, adjust the gas flow rate. It's important to be aware of the many variables in the MIG welding process that are controlled by the welder and influence a weld's quality. We'll discuss a number of them today, but training, guidance, practice, and repetition are needed to better understand each. Welding amperage or voltage is directly controlled by the wire feed speed, or WFS. Wire feed speed is measured in inches per minute, or IPM. An increase in amperage, in conjunction with the welding operator's travel speed, can result in an increase in the depth and width of the weld penetration, amount of metal deposited, and the weld bead size. DC polarity is described by the gun's connection to either the positive or negative terminal of the power source. The gun connected to the negative terminal is direct current electrode negative, or DC negative, shown in written form as DCEN. The gun connected to the positive terminal is direct current electrode positive, or DC positive, shown in written form as DCEP. The majority of MIG welding is done with DC positive because it results in a stable arc, low spatter, good weld bead characteristics, and greatest depth of penetration for the widest range of amperages. Arc voltage and arc length are directly related. Voltage is one of the two primary power source settings, and arc voltage is the measure of voltage transferred at the arc. Arc length determines the arc voltage. Arc voltage is set based on the transfer process and the shielding gas. Travel speed is the speed at which the weld puddle is moved along the weld joint by the operator. The travel speed needed for each specific welding condition is hard to predict based on various operators, but the results at the wrong speed are obvious. When the travel speed's too slow, too much heat is introduced into the weld, resulting in an excessively wide weld bead and poor penetration. When the travel speed's too fast, it can cause a narrow convex bead, insufficient penetration, and an inconsistent weld bead. Undercutting may also occur with faster travel speeds, resulting in a weak weld. Electrode extension, or stick out, is defined as the distance from the contact tip to the end of the electrode, which is controlled by the welder and the machine settings. An increase in the electrode extension generally produces a narrow, high-crowned weld bead due to the increased resistance, which lowers weld current and the heat available to melt the wire. Electrode orientation is the position of the welding electrode in relation to the weld joint. The orientation has a greater effect on bead shape and penetration than arc voltage and travel speed. When the electrode points opposite to the direction of travel, it's called backhand welding with a drag angle. When the electrode points in the direction of travel, it's called forehand welding with a push angle. Not all welding positions are possible for certain modes of transfer. The mode is determined by the heat input, the weld size deposited, and the shielding gas being used. For example, spray transfer is known for having a higher heat input and for producing a larger weld bead when compared to a short circuit transfer. To fight gravity, smaller weld beads are used in vertical and overhead positions. Short circuit transfers are useful in achieving this. The weld joint position and transfer process have varying effects on the shape of the weld and the fusion zone. The electrode diameter affects the weld size and the fluidity of the weld. A larger electrode requires high current to melt the electrode. The resulting wide bead of a larger electrode is larger and more fluid. Consequently, smaller electrodes are used for out-of-position welding. Other important variables to consider are shielding gas composition, gun angle, and gas flow rate. A welder must be able to strike and establish an arc quickly and easily. Now let's discuss how to strike an arc. An electric arc creates an intense heat near 6,500 degrees, which melts the metal at the joining point between the two items being connected. To strike an arc, position the gun over the joint and make sure your face shield is in proper position. At this point, you're ready to pull the gun trigger and start welding. The arc can be manually or mechanically guided along the joint as the electrode carries the current, or it may be a specifically prepared rod or wire that not only conducts the current, but also melts and supplies filler metal to the joint. It's important to note that once the arc's been established, maintaining the correct contact tip to work distance, or CTWD, or stickout, becomes extremely important. The stickout should be approximately 3/8 to half an inch, or 10 to 12 millimeters long. The easiest way to tell if stickout is the right length is to listen to the sound. If the stickout is too short, the wire electrode can fuse to the contact tip. It also causes the arc voltage to raise, resulting in a flat bead shape, increase in spatter, and possible undercut. If the stickout is too long, the electrode could stub out. It also causes the arc voltage to drop, resulting in a ropey and convex bead, increase in spatter, and possible loss of gas shielding. When laying a bead, make sure to maintain about 3/8 to half an inch distance between the tip of the gun and the material you're welding. Make sure to keep your work speed consistent, meaning do not speed up or slow down. Finally, to fill a crater or an unfilled end of a weld, pause or use a slight back step and release the gun trigger while pulling it away from the work spot. Large craters can cause cracks in the welding. Now let's take a brief look at the metal transfer process. The basic MIG welding process uses 3 techniques known as short circuit metal transfer, globular transfer, and spray arc. These techniques describe the method in which the filler metal or electrode is transported through the welding arc and into the weld puddle. In a short circuit metal transfer, which is commonly referred to as short arc, dip transfer, or microwire metal transfer, an electrical short circuit produces metal transfer. The electrical short occurs as the welding wire makes contact with the molten weld pool. The short circuit, or short arc, operates at low voltages and welding currents. A small, fast-freezing weld puddle is created, which is useful in joining thin materials and can be used in any welding position. Globular transfer occurs when the droplets of metal are greater in diameter than the wire being used. The metal is pulled into the weld puddle by the force of gravity. This method is typically used to weld in the flat and horizontal positions because the droplet size is too large and difficult to control in the vertical and overhead positions. A spray transfer occurs when the small molten droplets are detached or sprayed across the arc towards the weld pool by electromagnetic forces. This method produces very little spatter and is most often used on thick metals in the flat and horizontal positions. There are many advantages to the MIG welding process, including but not limited to the ease of learning the procedure, relatively simple cleanup depending upon the materials used, and its ability to be used on different metals. Drawbacks include the fact it's less portable, with shorter gun lengths, the gas can be blown away by high winds, and it's difficult to use in joints that are out of position. If you enjoyed learning about today's topic and have a passion or an interest in welding, then a career as a welder may be perfect for you. Welders use handheld or remotely controlled equipment to join, repair, or cut metal parts and products in a variety of fields, including construction and automotive. Nearly 425,000 people are employed in the welding and cutting field according to the Occupational Outlook Handbook, and more are needed. We hope you found our introduction to welding beneficial. Thanks for joining us at mycareertech.com, and a special thanks to the certified CareerTech teachers that assisted in building this curriculum. We'll see you next time.